Okay, so we are now starting a new chapter that is on entanglement and density matrix, and it is actually one of the another profound idea or profound aspect of quantum mechanics, which I think you have already learned that. You might think that okay, all the peculiarities of quantum mechanics we have learned already, but this is the one which is still there, and so I initially I was thinking I will go to perturbation theory from here, but then I realized it might be beneficial for you. So perturbation theory is nothing, it's also very important, but it is nothing but a sophisticated way to handle problems that you cannot solve exactly. But it is not it also will lead to something new, but these are entanglement and many body quantum mechanics are something that will give you completely new things, like very unusual way of thinking, and that might be helpful for you to think about your term paper. So that's why I decided to have those things before mid sem. That's how we do it every year, instead of doing the perturbation theory, which you'll do anyway, but by then you will be settled with your term paper topics, and then we can go on to do the perturbation theory. Okay, now unfortunately I wanted this class is kind of a very conceptual class, this initial when I start entanglement. And I wanted it to be a very interactive class, but I couldn't like it's quite interesting to it is quite nice to interact directly with various issues there, but be at least interactive online, then we can proceed in the same classroom type spirit. Okay, so we'll start with entanglement. But before I do that, let me ask you that what have you seen, what have you learned so far in your quantum mechanics course that that defines or that kind of separates quantum mechanics from anything else you have known. So in other words, I can ask you what is the essence of quantum mechanics that like distincts it from all the other kind of phenomena that you have studied. So, what do you think? You can be interactive and tell me what. Let's start listing them. Yeah. Yeah. No response. Okay, that's what I was afraid of. This class will be another usual online class. Nobody has anything to say that what is the thing as a distinct feature of quantum mechanics. Really?
Sir,
That's how bad it is.
sir,
Huh.
is it like you are asking like in terms of entanglement what we think?
No, I didn't teach you entanglement yet. I'm just telling you, if you know, you can tell. But if you know entanglement, you can tell. I'm just telling you, in your experience, what do you think are the distinctive features or signature features of quantum mechanics? What are the most unusual concepts or new concepts you came across?
Some like the quantum mechanical phenomena what I have observed till now is like most of them, like many of them are in such a way that our classical intuition does not follow, like does not
Yeah, yeah, of
coincide with.
course. That is the generic statement, but be more specific.
Like the principle of superposition.
That
That's
is that is one of the most profound thing, of course. Okay, what else?
compatible and uncompatible
So
observables.
this leads to this. Okay, let's say list it separately.
The uncertainty principle.
So this is a consequence of this, or you can say other way. Okay, yeah. What else? Good. Now we are rolling.
One more thing that I found astonishing is that in classical mechanics, if a particle does not have like if it in the particle in the box problem, if it does not have in classical cases, if a ball is inside a box, it cannot cross it. I mean, if it does not have the required potential energy. But in
Ah,
quantum mechanics, there is always a probability that it can, like the transmission tunneling. Yeah.
okay, good, very good. What else? Good, we are rolling. Continue. What other phenomena have you came across? Yeah, is there any problem in the main camp, in the permanent camp, in the temporary campus with broadcast or anything? I can't hear you. Can you hear me? Is there a problem with connection?
Spin on itself is a new, I mean, the definition of spin is very different in quantum.
Spin. Okay. Yeah, that is one point. Very good. This is,
Now
yeah.
it's audible, sir.
Yeah, now it is audible. Yeah.
Okay, sir. Fine.
Okay. So far you guys didn't get to interact. So why don't you say something? I know maybe what you wanted to say is already being
Sir,
told. Yeah.
so discrete energy states in case of quantum mechanics.
Okay. Discrete. Or quantization.
Yes, sir.
Okay. So this is the thing. Interestingly, the name quantum mechanics came from this. Okay, quantization. Okay, because this was the first experimental observation, first strikingly something different from classical predictions. But this came fifth in your mind when you describe quantum mechanics, and that is because it is not one of the most quantum thing at all. Quantum mechanics just got its name for a historical reason, but quantization or discreteness is not a. It happens even without quantum mechanics elsewhere. Right? So it is not the signature of quantum mechanics, but quantum mechanics sounds cool, right? If you could, it's not easy to come up with a name based on superposition. What will you call it? Anyways, what else? Naming something is important. It should sound cool. Okay, what else? We just learned some of these things this time, this course, this quantum mechanics 2 course.
So time reversal.
So
No,
tide reversal is also there. That is a different. That is a formalism. We learn
sir,
how
we
to set
can.
up quantum
So
mechanics.
the place where we learned about that we can about those gauge fields. The
So
like
gauge field.
without even electric and magnetic fields, we can still
So one main thing is
like the idea of potential is different in
role
quantum
of
mechanics.
okay gauge.
Potential is not an imaginary phenomena in quantum mechanics.
So the experimental manifestation is Arnold Bohm effect. Okay, what else?
So the idea where we learn that in case of quantum mechanics, the vector potential has a meaning.
Yeah,
That
that is what I just wrote it down here.
okay.
What else? Okay, can you elaborate more about spin? So notice that spin had two things. One, so spin is peculiarity at two levels. One is uh, the main peculiar thing is spin half integer. Okay. Now half integer is why it is peculiar, because even though I can explain the behavior of half integer spin in terms of rotation, it is still a question that well that question I am not going to address here, but that how electron generates spin half, right? That is still question that requires quantum electrodynamics. But even if I said, let's say somehow it is generating spin half, then the behavior of spin half is something I understand, because I know this kind of thing in classical world in the form of spinors. That, as I said, that spinors are this kind of object. Let's say I have this, yeah, this object. So what is the front side? Oh, this is a symmetric object. So let me take some asymmetric object. Yeah, I don't have apparently anything asymmetric here. Okay. Anyways, so as I said, that it is something that it doesn't rotate it doesn't rotate itself back in 360-degree rotation, but that it rotate itself back is the 720-degree rotation. And we have given this example with a objects with one hinge like spinors. Now spin we just learned in previous day, it is not just that, it is one thing more than that, that it requires to be uh, also under time reversal. It doesn't come back to itself after 2 time reversal, but for it requires double of that. So that is strange, that doesn't happen in any classical object. So that is what makes spin inherently quantum object. Spin half integer makes it an inherently quantum object that doesn't have any classical counterpart or any classical relation with anything else. Okay. Okay. Anything else you can think of now? Now that you can list that, then you have kindly you have hopefully have a rough understanding of how quantum mechanics is going to be different. And of all these things, the most important thing is superposition. That is the most strange thing, and that is what is almost alone responsible for other producing many other things. Not all of them. Like for example, you cannot just say spin is because of superposition, but it is a peculiar thing on its own. But let's say, is there anything else you can recall? So this one is basically the role of wave function and potential. This is this point. Okay. This is a good time to revise your whole understanding of quantum mechanics and see that what new things you have learned here that you couldn't have imagined elsewhere.
So also here we deal with the probabilities. What are the
That kind of comes from superposition, but yeah, this superposition, by that I mean the superposition of quantum mechanics, not the classical, where you need this wave function and probability amplitude and not the probability. So that kind of inherently inbuilt in there at that point. But yeah, it's a good point anyway. So let me put it as measurement, right? The problem of measurement, which means what you mean to say that when you measure, you only talk about probabilities, but probability amplitude is the thing that controls that, right? Yeah. So that comes under this superposition point. Yeah, good point. What else? That's what you mean, right?
Yes.
The concept of measurement and collapse. Yeah.
So the concept of projective theory.
So that is also a product of that. The projective theory. That is a very important point actually. That quantum mechanics is a projective theory, which means the objects that you deal with in the object that you are calculating, or that everything that you used to describe, that is not a measurable object. Now that doesn't mean exactly projective theory is a rigorous mathematical description, but I am telling you colloquially that how it is different. That your whole theory is formulated in terms of wave functions. But wave functions are not something you measure. What you measure is square of wave function, the probability. But wave function dictates that what you measure, and dictates the probability, and that's why you get the concept of interference and all that, which is superposition. And it becomes projective because you are dealing in your theory is in terms of a non-measurable, which means there is some degree of freedom that what you can choose such that the measurable remains intact. Okay? So that makes many things different. That is the reason why the symmetry description, the discrete symmetry description, all these things we learn, they always has this projective feature as highlighted everywhere, right? Whenever we are constructing the action of a symmetry, we are asking how the symmetry, how that operation is changing or manifesting in the observables. But the theory is built in terms of something that is not observable. So it has some flexibility to set it up in a way such that the observable remains intact. Right? So that is the meaning of projective theory. And this is a very important point. and this projective feature is highlighted everywhere. So yeah, so I can actually make it a separate point that this is a projective theory. Although projective theory are also like there are classical system which can be described in terms of a collective excitations can be described in terms of a gauge theory and all that, but they are like such as nematic orders and many such topological classical systems are there. So but that is not that it doesn't happen at all in anywhere else. It's not a uniquely quantum phenomena, but it is one of the highlighting phenomena of quantum mechanics. But quantum mechanics has another very interesting point that tells you that your original theory constructed something that you cannot measure directly, but it controls what you measure. And what happens with wave function and potential is particularly interesting. There we demonstrated that the potential interacts with that object directly as such that it changes all the observable. So it is, you cannot really call it a completely although it cannot measure it, it is important, right? It is the controlling factor in your theory. And why you cannot measure it, that we don't know, but how it is protecting itself against measurement, that we discussed in great length in previous semester, like uncertainty principle and all that. They are how they are keeping this thing intact, that as you try to measure, come closer, then uncertainty comes in place, and you start losing information elsewhere. Okay, good point. So what else? Okay, good. So now we have covered a something very interesting. Okay, it's a good exercise. I think now you have forced to think about everything in one go. Everything you have learned till now. Yeah. What else can you think of? So notably, these are the things. Almost all these development, or at least many of the developments, are directly observable in experiment, like superposition, as we have discussed entirely in terms of experiments. And they are all manifested very clearly in experiment. That is why, that is like physics is at the end of the day, it's driven by experiment. So you have to your whatever theory you might construct all beautiful theories and all, but they has to be physical, right? They have to be measurable. You have to think in terms of measurables. Okay? So all these phenomena have very beautiful experiments that explains and demonstrate them. What else? Okay, good. So this is more or less almost everything I think we have learned so far. And one more thing we have noticed: this is not again is not something I would say as a separate point, but that the fact that you require complex numbers, to explain a quantum wave function. Okay? Complex number to explain wave function. So we have demonstrated this in term using the Stern-Gerlach experiments, and also by the logical argument that why your wave function you should generally work in a basis that it is unless you want to go in some special symmetry basis, that even a plane wave you should explain it in terms of e to the power ipx, but not sine px and sine e to the ipx by h bar, not cos px by h bar or sine px by h bar, because of the fact of because when you bring into time into this, you can show that there are scenarios where the particle can vanish from everywhere and violating mass conservation and all that. So this is one main point, that you need complex number. It's not a choice. Okay, so you need complex numbers to describe quantum mechanical theory. And interestingly, the dynamical equation. So this is a separate point, but it is. I am not saying it is distinctly quantum. So oh, what happened? Yeah, this is a problem because my phone gets coupled to my laptop, and whenever a phone comes, everything gets interrupted. Okay. So you can see my screen, right? So the dynamical description has a single derivative in time and double derivative in space. This is another thing we learned, and that is not it is not that it happens only in quantum mechanics. We know that in heat equation is like that, but heat equation doesn't have but heat equation doesn't have imaginary numbers. So that is what inherently quantum, and it is worth keeping in mind, and it could be some of term paper problems, that techniques used to solve heat diffusion can be with some care can be handled to describe quantum dynamics. So this is the technical point, and there are things called diffusion Monte Carlo, and that people developed initially for heat equation, but then they use it for quantum mechanics. But the eye needs to be this eye needs to be handled with care, because this eye can create heavy nuisance, because when you square stuff, I square becomes -1. There are 6 scenarios, and if there is a scenario where you have to square it, cube it, and then they start fluctuating in sign, that doesn't happen in heat equation. Okay, so then that creates a problem, and there are ways to handle that. Okay, so this is basically, and there are scenarios where that cannot be handled, and that is also very interesting. That also is notable. Okay, so this is another distinct feature of quantum mechanics. Now, as I also told you earlier, that there are 9 formulations of quantum mechanics, 9 ways to describe quantum mechanics. All these factors, all this reality, and we have learned in the previous semester only 2. So those 9 ways are basically wave mechanics, so now we talk about formalism, wave mechanics, matrix mechanics. I don't remember actually all of them, or density matrix, path integral, and so on. I'm not listing because I don't remember all of them. There is semi-classical, etc. So in this course, we previously learned this. In this quantum mechanics 2, we will learn density matrix, and I think that will be roughly all. It is worth learning path integral, which some of you can take up, but that is basically all. So now what we will learn in this course, in this chapter, is another new feature of quantum mechanics that will kind of start shaking your idea about everything. Okay? So this thing is called entanglement, and this is basically it's a conflict between realism and locality. So what is realism and what is locality? Let's just quickly understand these two, and we will see that how we will now set up the discussion on entanglement to see that how it messes with these two ideas. So realism is a philosophical is the name of a philosophical idea. It tells you the state of something is whatever it is, irrespective of whether you describe it or how you describe it. Right? That is basically this is actually all these definitions were designed by Greek philosophers and all that. But the simple idea is whether you observe something or measure something, that doesn't alter the fact what it was, right? And that is what we know. That is what we believe in. That is what makes sense. Right? Whether I observe, there are all poetic interpretations of these statements. It says that if a dead tree falls in the forest and nobody observed it, then nobody was there to, then does it make sense to tell that it produced some sound or something? And of course we know that it must have, but sound is basically vibrations of air molecules and all that. But whether some ear have received that, detected that or not, can we define it as sound or define it as something else, and all this, if you go to a philosophy class, they will spend hours debating that. But the idea is we don't do that. So we will just stick to the belief that what is realism? Realism nothing but state of something is independent of whether it is observed or not, or how it is observed, etc. Now locality tells you is causal relation. Causal relation means what happened at this point, at a particular point in space and time, must be must be an effect of something that happened before in time. So the cause must precede effect. That is the simple logic. Okay? Cause cannot simultaneously occur with effect, and by simultaneous I mean people call about instant reaction of something, right? But it is instant in a colloquial sense, but nothing is instant. It's always something happens, you receive the information and react. Right? It cannot be like you immediately react. There is always a timeline. So you have to first receive the information, you have to know that what to do. You might be very fast at it, but you cannot be instant. That is and even if if you design the most precise machine, it cannot be instant. Okay, at least the signal has to travel, right? That something happened, let's say, that information have to travel to you first, then you react, right? You might be very fast at reacting, but there is a traveling time of information exchange. So this idea is locality, simply the causal relation, between event. Okay? This is called locality. So what happens in this? So in this class of phenomena called entanglement, it was these two things were came into contradiction with each other, and eventually it led to a scenario that boils down to doing. So let me tell a little bit about the history of this subject. The history is very rich, and the sociology is even richer. Okay, so the history is that actually I prepared some slides for it. So let me see if I can share the slides with you, because this year entanglement won Nobel Prize. So I was asked to give talks at various places on this, and so for this reason I have some slides. So let me try to find the slide. So I'll share with you. Although it might be, I was thinking whether to show you the slides, because those talks are, one talk I was giving for all people. All people means all science people in ISAR, and another talk I was giving for in the regional science center in Tirupati, which is for all college kids of Tirupati, right? But you are supposed to be much more advanced than both this set of audience. So these slides are very trivial for you. You are like taking my quantum mechanics course, so you are supposed to be much more advanced. So it might turn out to be, but it's fun to go through the history of the subject. Then we'll talk about it. So what should I share? Okay. So I don't know if any of you are familiar with this movie. I don't know if anybody watches that anymore. In our school days, or not even school days, in my college days, I actually watched this. Did anybody watch Star Trek? Any of you?
I've watched the new movies. That's
Nah,
all
new
I've
movies are crap. Don't watch this. Watch the old ones. With Captain Kirk were played by William Shatner, and Leonard Nimoy played the Spock. Okay, so the old movies will might look bad if you look at the animation quality. Of course, the best special effect was not that much, but those 7 old movies, they were a pure gem in terms of concepts, right? One of them talked about a collective consciousness of, okay, I can give a whole talk on that movie, those movies. So let's not get into that. Okay, all this collective consciousness, very ahead of time concepts they have used. Okay, you may not like it after in terms of special effect, but once you start watching it, because it's 70s 80s special effect, right? It's nothing compared to present day, but they are brilliant in their ideas. Okay. Anyways, it had this thing called, if you, some of you have watched, they had this beam me up. It tells that so Captain Spock tells that beam me up, and then they turn on some device and they can move one physical location to another location without traversing the physical space in between them. So this is called teleportation. And one of the Nobel Prize winner in this year, Anton Zellinger, he was the person who were able to no, of course he didn't teleport human, neither he teleported mass. If you teleport mass, then it causes, then you have to deal with local mass conservation problem, so it's not a easy, I don't think it is possible. But what was possible, that they were able to teleport information, which means you can send the information about the state of a particle, quantum state of a particle, from one location to another without traversing the space in between. So which is quite fascinating. Even if you cannot teleport a human or a mass or an object, you can at least teleport information of state without, which is, if you think more about it, it will appear really fascinating. How can you go from, it is a send a, it's like sending a mail from one place to another without traversing the space in between, which means no where, no airspace, nothing, no travel of information. So so he is one of the Nobel laureate. His Nobel Prize was because of that. And I always start this class, these lectures with this warning sign. Okay, so when I was a postdoc at Columbia, there I met some friend of mine once showed a professor and said he had done some crazy stuff few years back. And the crazy stuff was he entered in a class and started playing 9/11 footage, started stepping and attacked some stuffed animal, and everybody gone crazy. I mean, what the hell he is doing? So then university, some students complained, and university launched a investigation. And then he was asked, why did you do that? And he said, I was given 1 hour or small few hours to teach quantum mechanics to some people who never learned it. And I saw there is no way I can do that. But what I can at least do, that make them, give them a shock and tell them that this is shocking. Okay. So that's why I did all that. So eventually the investigation said, okay, you can go. They didn't punish him or anything. And it made sense to him. Okay. And I think this is which makes sense to me also. Like, so what he said is, in order to learn quantum mechanics, you have to strip to your raw, erase all the garbage from your brain and start over again. And then he also said that nothing have you learned so far help you to prepare for this, because things are going to contradict everything. Okay, so I don't need to tell you that to you now, because you have already know that it's a useful message for someone who is first time taking the class. Okay? So and you know that what are the main problems with quantum mechanics? The problem is there are no analogies, no good analogies. And we all learn quantum mechanics with analogies, right? And not quantum mechanics, we learn anything with analogies. For example, you have learned in physics, let's say if I put a hot object with a cold object, the heat flows from the hot to cold object, right? And there is an analogy for that. The analogy is like that: if I take two water tanks, one has higher water level than other, connect them with a pipe, water will flow from one tank to another, right? And how fast it will flow and up to what it will flow, it decided by till the point the water is coming to level, right? So you can use temperature like water level. So this is a beautiful analogy, works perfectly. At quantum mechanics, there is no analogy. If you try to give an analogy, it will be always wrong. So we used analogies knowing they are wrong, because there is no other way. And that's what confuses everyone. And the second thing you know in quantum mechanics is misleading semantics. It's like full of contronyms. You use the one word for another thing, and that means completely different things. You know all this now. So these are the two challenges generated in quantum mechanics. And this, you know, these three people won Nobel Prize this year for the experimental verification of entanglement. And so let me get a little bit to the history, but just tell you that where the so it's particularly encouraging to teach this chapter this year, because it won just won Nobel Prize. And you know, if you ask your senior, so for last 3 years during this class, quantum mechanics one course, usually the Nobel Prize is announced. From the beginning, I am betting with the student this year, Align Aspect will win it. And every year he is not winning it. And this, last year I didn't say that because I thought, okay, what's the point? And then he won. And Align Aspect, you have already studied one of the experiment of Align Aspect as an assignment problem in Quantum Mechanics 1 course. And that experiment was on single photon interference. He showed a single photon can interfere with itself because it can travel in two different paths at the same time, and there can be interference between these two traveling paths at the same that it takes at the same time. Okay? So this is a fascinating result, one of the most cornerstone results in quantum mechanics. So that is what was your assignment in quantum mechanics 1, if you remember, to study and formulate that experiment. And I will come a little bit about the history of the subject. So these were the papers that were acknowledged in Nobel Prize. So let me skip this because you already know the history of quantum mechanics in early history. But here is the history of entanglement. So, so around 1935, so Einstein, Podolsky, and Rosen have came up with an idea. So that idea I'm going to explain in detail. Came up with a thought experiment that kind of tells you that either realism, so that tells you that realism and locality contradicts each other. Okay? If locality has to be there, you cannot have realism, and if you have realism, you cannot have locality. And that kind of is very, very bothering because both are sacred. Like cause precedes effect. It's a very basic thing. You cannot keep it. You cannot throw it out. So this was so quantum mechanics is not just challenging your notion of realism, it was already challenging notion of realism. It is already telling you that it can be in various different states before measurement at the same time, which is already anti-realism. But if that is true, so this Einstein-Podolsky-Rosen thought experiment tells that if that is true, then even localism is challenged. Okay? So that was the main point. And so then they came up with two resolution. One is either quantum mechanics is wrong. Of course, that resolution is hard to proceed with because by then there are plenty of experimental other experiments that happen that tells you quantum mechanics cannot be wrong. Okay? But there are also many experiments that also happen that tells you localism cannot be wrong either. So if they two are contradicting, then one of them has to be wrong at some level. So then Einstein's idea was that quantum mechanics is an incomplete theory. So it has some hidden variable that we don't know about, and because of that, it is leading to this kind of a strange conclusion that is contradicting localism. So that was his proposition, and that was 1935's paper. And Einstein was a celebrity by that time because in 1905 he had this special theory, and I think 1915 he had this general theory. And Arthur Eddington already have proved by his solar eclipse images that they are correct, and he was a celebrity. So whatever he did became a news. So then there was a news in New York Times that says Einstein attacks quantum theory. So anyway, so then this problem was kind of untouched for a long time. And the reason was that it was a very difficult problem and you don't know even where to start from. So this is also another interesting point to consider. Sometimes we know so now what we are learning about quantum mechanics, all the assignment problems you do, all the exam problems you do or anything, they are very easy problems. Why? They might be difficult to solve. I'm not saying that. They might be long, lengthy, but it boils down to a differential equation or a matrix equation, how hard it can be, right? It's conceptually easy, right? So it's kind of, and that is what is the triumph of quantum mechanics, that it was able to convert such a like not just quantum, that is the triumph of people who worked in who formulated quantum mechanics. So they were able to convert a strange set of experimental phenomena to a theory and eventually to a machinery that any stupid can calculate what is going to happen in the next experiment, right? That is the beauty of this theory that you are learning now. Okay? So now the problem is this job turned out to be very difficult in this entanglement problem, because people didn't know what the problem is clearly. They cannot formulate the problem. They cannot bring it down to some equations that they solve and they say, okay, this is right, this is wrong, right? You don't know that. So there is a famous quote by, I don't remember, I think Fermi or Pauli, one of them said that. They said it's not even wrong, which means they read some theory. If it is wrong, you know it's wrong and move on, right? But it is not even wrong, means he realized it's not right, but it is neither wrong. So when you do research, you are often stuck in that pocket. That you know what you did cannot be wrong, because you might have started with some idea which was well established and correct. And then you are stuck somewhere that you cannot prove it wrong either, and neither can prove it right. So if entanglement was in such a zone of discomfort, that Einstein proposed a thought experiment. Explaining that thought experiment has three propositions. One is either localism is wrong, localism is not true, either realism is not true, or both of them are not true, or quantum mechanics is not true, or quantum mechanics is incomplete. These were the four possible paths they left with. Okay, and none of this path, and it is not easy to figure out what can I do precisely, because you have to bring down all abstract philosophical statement to a level of measurables, right? What can I do? What can I calculate? What can I measure to say this will happen if this is right, if this will happen if this is wrong, right? That was the challenge. That was the problem for a long time. That's why nobody touched this problem. Maybe somebody tried, but nobody succeeded. So the man who were able to crack in this was John Bell. So he was a physicist at accelerator designer at CERN, but he was working mainly in engineering theoretical aspects of that. And he were attracted to this problem for a long time, and eventually in 1964 he was able to bring down this whole problem in a concrete footing, in a formalism. And he said that if this is true, this will happen. If that is true, that will. So we'll study Bell's inequality today. So not today, in this chapter. So this is called Bell's inequality, which was a precise, crisp test that tell you if this is true, if realism is true, this must hold, realism or localism. If not true, this something else must hold. Right? So it was the first hack on the problem. And then, and he actually, if he would have been alive, he would have definitely won the Nobel Prize this time. But he passed away quite a while ago, I think. So then, the first experiment on that was by Clauser, and they were one of the Nobel laureates of this year in 1969. And they were the first time to. So Bell said there is an inequality which must be satisfied if you respect locality and realism. So they found violation of this inequality. But that doesn't mean yet quantum mechanics is correct. But it tells you that you have to give up either localism or locality or realism. Okay? So that is what Clauser's experiment suggested. And this experiment had many loopholes. So of course people improved those loopholes. He himself and other people like Alain Aspect and all improved on this loophole, and they kind of eventually it went back till 2017, and for a long time completely loophole free test that closed the whole door on this EPR issue. They says not only it is it is violating localism and reality, so local realism and locality, it also satisfy whatever quantum mechanics is predicts, which means quantum mechanics is complete. It's not an incomplete theory, or there is no hidden variable question, and it is and it violates localism or reality. Okay, so this is basically the saga of this subject, and that's why it won Nobel Prize. Now it came at the brink of technology because people are able to teleport information or do entanglement over hundreds of kilometers in satellite communication, and that is why it was given Nobel Prize, because usually for Nobel Prize you need a verification that it can be used directly for human life, to change human life. And even though we physicists knew this is one of the groundbreaking discovery, and it kind of alters how you view about the world, Nobel committee will not care about it unless it is practical. Okay? So that's why it won Nobel so late. So this time also, uh, somebody was asking that is this year Nobel Prize is also something for a new technological development or fundamental? Then I said it's fundamental, and it is the most fundamental thing ever. And then that person was very surprised. They said that there are still prizes given in fundamental physics, which means they thought that there are no more fundamental physics left to be prized, but that is not true. There are many fundamental work, and actually there are these quotations that says that Bell's theorem is the most profound most important work in history of physics. Somebody made that statement. It may or may not be. One can say you may not isolate it as the most, but it tells you it's really changes the ground of everything. And the second one somebody said is the particle physicist from Berkeley. He said that it's the most profound discovery of science, not just physics or anything. And you might understand why. Somebody might say, okay, why not discovery of some drug that saved millions of human life? Of course, you can always debate, and there is no conclusion to debate. So I will not enter there. What is most important? You cannot say it like that. But if you think that something that completely completely changes that what you think or what you believe is reality, it's pretty important. At least it's kind of well, important or not. What is important is difficult. In fact, quite surely, maybe a vaccine is more important than Bell's inequality. Of course, it is. It's not maybe. But what is more profound or what is most profound, that one can debate and all that, right? So it is probably in that sense it is being told. So don't take these statements like that kind of. It can be always debated, somebody's personal opinion, but I'm just giving a perception that how big deal it is. Okay? And two more interesting anecdote was when Bell was when Alain Aspect was planning his experiment. He visited CERN to talk to Bell to ask him that what does he think, how it can be done. And first thing he asked, do you have a permanent job? Because it's a difficult problem, and it may happen that you work 5-10 years and found nothing. And then if you don't have a permanent job, it's very difficult for you to find a job. So if you have a permanent job, of course they cannot fire you. Okay, so that was the kind of the status of the problem at that time. And he used to say that I am a quantum engineer, which means he was designing particle accelerator. But on Sundays I have principles, because again nobody is going to pay you or going to reward you for thinking about something like this at that time. But they thought about it, and that is where here we are, and that is why we can think of a technology that is dependent on that. So, but you know how funding mechanism jobs work like that, work differently, and profound discovery doesn't come as a product of that machinery. Anyways, so this was the history of the subject, and there is one more interesting point. So David Marmin at some point of time got very frustrated about the situation, that it's a thing that was bothering him, but nobody is thinking about it, nobody is doing anything about it. So he was very frustrated, so he wrote a poem. Okay, the poem is you can go through the poem. I'll send it to you separately, but there is not much time to read a whole poem, and the poem is very bad. I mean, but it's okay. I mean, it's a physicist poem, how good it can be. But let's just look at the last paragraph. That kind of tells you what he meant to say in the blue. It tells that I cannot define the real problem, because the problem was formulating the problem for a while. Therefore, I suspect there is no real problem. But I'm not sure that there is no real problem. So this was kind of the level of confusion. And he said that there are two types of physicists. One is those who are bothered by it, and he was one of them. And type 2 are those who are not bothered of it. And both of them are wrong in some level. One of them completely misunderstand the main point and of EPR. And the other of them says that it's solved, but they cannot explain how it is solved. Okay, so this was his take on this. So yeah, so first statement was that, as I said, this is realism, that which are known or perceived as existent nature, independent of anyone is thinking about or perceiving them. Okay, so let's skip this and come to the point that how it was. Okay, let's not get to that, but let's tell you a little. Let's get a little more technical, and tell you about what is the EPR. What is the main point about EPR and how one can think about it. Okay? So okay, as an interesting matter of fact, so Bell had a postdoc called Bartleman, and who used to wear two different color socks in his two feet. And you can Google him. There is a picture of him. He's also a very accomplished physicist. His Wikipedia page has his picture with two different color sock, and he wrote an article to explain the Bell's inequality in terms of his socks. So let me tell you quickly, explain it in terms of the socks. Then I'll tell in terms of the spins. So the idea is following. So Bartleman is a guy who wears two different color socks in 2 feet. By the way, you can do this whole thing also same color sock, but it's just how Bell wrote it. Okay? So let's say if Bartleman is entering through a door. Okay? Bartleman is entering through a door. Bartleman is entering, and you saw him stepping into the room, and you saw he's wearing a red sock in that feet. So since it is Bartleman, you know immediately the other color is not red. It can be something else. Let's say there are only two colors available, white and black. Make it boring. And if you see it is white, other one has to be black because Bartleman wears different colors. It's a normal person, you will know that they are same color. There is no mystery. So now let us try to set up a, a state which is, let's say, a pair of socks. They are prepared in a state that they can be both red and black and white at the same time, and there is a pair of them. Okay? So now you know they can be. So if they are spins, then what will happen? So imagine I have a spin, a pair of spin, and I want to prepare a state which they are either have to be opposite. They have to be opposite. So how many ways it can happen? The first spin is up, second spin is down, right? Or the second spin is up, first spin is down, second spin is up, right? These are the two possibilities. I said the rule. The rule is the total spin is 0. Let's say the total spin has to be 0. So that means if one is up, other has to be down. But it's a superposition state, right? So you don't know which one is up and which one is down. So it must be in a state that is an equal superposition of up, down, minus, down, up. Okay? You could have done plus also, but you know this is a singlet state, and singlet states have this minus. So this is the, if you give the sock analogy, it is white, black, minus black, white by root 2. Everybody get this point? Yeah, did you get the point? The description of the state? What? You've never seen singlets, or you are confused?
Yes, sir.
Okay. So now let us say somebody have prepared such a state. So let's call that guy Charlie. This is the usual name given in this literature. So Charlie have prepared a state of spin 0 with 2 spins. Now that means what Charlie has is a up down minus down up by root 2, such a state. Or you can say Charlie have a pair of Bartleman socks, but in a quantum level, which means if it is a regular sock, Charlie will have a white black pair. Now Charlie doesn't know which one is which. So let's first talk about the classical experiment. Let's say somebody prepare a state and send one copy to a person called Alice, another copy to a person called Bob. So let's say this guy Charlie has a pair of such socks which is black and white. Now it is classical, means one of them is white, one of them is black. Definitely, no superposition. So then what Charlie does, he sends one to Alice, one to Bob, without knowing what is what. Okay? Without knowing what he said. He has it in a closed box. He doesn't look at the box, it picks it up and put it into other box, and then send one, post one to Alice, one to Bob. Okay? They are located far apart. So let's say Alice got her box and opens it, gets black. That means Bob, if he opens his box, will definitely get white, right? Okay. Or alternatively, if she gets white, they will get black. Okay? A priori, nobody knows. There is a 50-50 probability, and it can be black or white. And if one of them gets black, other of them will definitely get white. Okay, everybody got this picture? Is it clear so far? Yes?
Yes,
No?
sir.
Okay. Now let us okay, so now time is almost up. So let me ask you to think about this. Now imagine, instead of this black-white classical pair, if Charlie had a WB minus BW, so let me state it like this: WB minus BW by root 2, which means it is black or white, but which one it doesn't know until somebody measured it, right? Until somebody measures. So then he prepares to a state like that, or you can think in terms of this if you like it. Send one of them to Alice, one of them to Bob. Now notice what is the difference between these cases. In the classical case, when Alice received the box, what was inside that was already that, right? It was already black or white, even without measurement. She opened that and found it black. Now in this case, before the box is open, it is just like the cat experiment, dead or alive. It is both black and white at the same time until measured. Once it is opened, then it is measured, then it becomes black or white. So that determines what it happens here, right? Because if you open and found it white, that means it have collapsed into this WB state. So that means it has to be black. Or if you open and find it black, it have collapsed in BW, so then it has to be white. Okay. So now try to think about this. So now it sounds to be similar, because one is black and another is white anyway. But here the only difference is until measurement you don't know that. In other cases you knew that even without measurement. You just didn't know whether it is black or white, but it was black or white. But in this new case, in this quantum case, you just don't know whether it is black and white until measured, and there is no way to know that, because that's what superposition tells you. So now think about it, how these two things will change. What will be their difference in observables? Okay. So that is what brings us to the PPR paradox, and that is what we'll extensively discuss in the next class. Okay. More questions? Questions, comment? Did you understand the difference between these two cases? Classical and quantum. Yeah, are you saying something in the temporary campus? Okay, if none, let's close the class here. Next class we will discuss about that. But go over this and try to understand that what will be the observable difference between these two cases. Okay, in one case you know it is black or white, if whether you measured or not. One is a classical probability, another is a quantum probability, that it is black and white at the same time until measured. And once you open, it collapses into one of those two states. So how these two phenomena will manifest in this setup, in this process, where Charlie prepares a state, send one copy to Alice, another to Bob. They open their boxes or perform measurement, and they see whatever is there. Okay, good. That's all. See you Monday.